Hi, and welcome to Allen High School's discussion of states of matter solutions and intermolecular forces. We're just tying together some loose ends and introducing a few new concepts. So let's move forward. We're going to look at some more qualitative types of questions. This would be the type of question you might see in part B of your free response after you've given up your calculator. Now, an assertion is made. This is a claim. Here's the claim that it takes longer to cook an egg until it is hard-boiled in Denver, altitude of 1 mile above sea level, than it does in New York City. Justify that claim. That's the goal here. Well, the first point we want to make is that a substance will boil when the vapor pressure of the liquid is equal to the barometric pressure. That's the definition of boiling. The normal boiling point is when that barometric pressure is 1 atmosphere. So 2, if we decrease the pressure of our barometer, our barometric pressure, that means that the vapor pressure is going to reach that barometric pressure at a lower temperature. In other words, the boiling point in Denver is less than our boiling point in New York because it's at a higher altitude. So this is being a little bit more explicit. Well, if you decrease the temperature at which you are cooking the egg, then it's simply going to take longer to cook. It's a rate issue, really. It takes longer to cook. So that's that justification. All right, burning coal leads to acid rain. Well, coal contains sulfur. When that sulfur gets into the air, sulfur in the oxygen can make SO2. Actually, with enough oxygen, it can also make SO3. This is a nonmetal oxide. In the presence of the moisture that's in the air, this is an acidic anhydride. Remember, we just learned those reactions. So any SO2 is going to make H2SO3. And if SO3 is ultimately formed by the addition of more oxygen, we would make H2SO4. Hence, in the air with the moisture, we have acid. And that acid can get on vegetation and buildings and destroy them. And that is still happening in some of our countries. Not as much the developing countries. We've made some progress in diminishing the amount of acid rain. Okay, perspiring is a mechanism for cooling the body. Well, perspiring means we're taking liquid off of our arms and the sweat that's pouring out of our arms, and we're vaporizing it and going to the gaseous phase. Well, to do that means we have to break intermolecular forces. Well, breaking intermolecular forces, breaking any force of attraction, breaking bonds requires energy. So since it requires energy, it's endothermic. Where's it going to get that heat energy from? The heat energy is pulled away from the surroundings. Right? An endothermic substance takes its energy from the surroundings, your skin. Okay, so heat's taken away from your skin and the body feels cooled. All right, the addition of antifreeze to water decreases the likelihood that it will freeze. Well, if we take a solvent and add a solute, we're going to get a solution. And solutions always experience a freezing point depression, a negative change in freezing point. So the freezing point of the solution, that means that the freezing point of our solution, it's a colligative property. The freezing point of our solution is less than the freezing point, whoops, there shouldn't be a delta there. The freezing point of our solution is less than the freezing point of our pure solvent. So it freezes at a lower temperature. So hopefully it will stay in the liquid phase to a lower temperature and not crack our engine. which unfortunately is what happened to our boat one summer when my husband and son did not winterize it. It cracked the engine, and he had to replace that engine. It was not a fun summer for my boy. Okay, putting rock salt on an icy driveway melts the ice even when the air temperature is minus 10 degrees. That is the same concept. All right, you add rock salt. Rock salt is typically, they'll often use magnesium chloride. You can certainly use sodium chloride, but magnesium chloride has I equal to 3. The number of particles is equal to 3. That's a simplistic way of looking at I, and I equal to 2 for sodium chloride. Okay, so when you add that to water, you're going to decrease the freezing point. That means it's going to melt at a lower temperature. So that's the goal, to melt the ice on the sidewalks so little old ladies like your teacher don't slip and hurt themselves. All right, let's take a look at our next one. All right, the normal boiling and freezing points are respectively. What we're going to be doing is drawing a phase diagram. Unfortunately, this is one of those things that AP is phasing out. We taught this in pre-AP chemistry, and I knew I would have an opportunity to go over it now. I like to call this, I learned this at an AP conference, you know, the good old butt diagram. So what you have in a phase diagram is looking at pressure and temperature changes. Now it gives me the normal boiling point. So normal means at, let's put that in a different color so we can see that, at 1 ATM. So at 1 ATM, we have a freezing point and a boiling point. So the boiling point is given at, let's do the freezing first, 84 Kelvin. So 84 and 85, 86, 87. Let's call that 87. So this is my boiling point, and this is my freezing point, my normal boiling point and freezing point. Now it gives me my triple point. My triple point is at 82, so it's going to be down here. This is 83, so 82. Should have drawn this over a little bit more. But let's call it about right here is my triple point. Okay? Now, how you draw the diagram is we're going to have an equilibrium point from here to here, an equilibrium from here to here, and then it's below that and everything below that. And I'm a little off scale, but as long as you label everything, you're going to be okay. So that's my triple point. That's my freezing point. That's my boiling point. Okay, and now we want to label the states. Remember, this is a butt cheek, that's a butt cheek, and that's the bum crack there, and this is the gas. And this is solid, and that's liquid. So solid, liquid, gas. Okay, and so that's roughly your diagram, and that would be acceptable as long as everything was labeled on here. Now it says any changes that can be observed when you take a solid argon and increase it from 440 Kelvin to 160 at half of an atmosphere. Well, we know we're below, somewhere below this triple point. So we have our solid, and we're below the triple point, and we're crossing underneath the triple point. So we're going directly from solid to gas. And that is called sublimation. So it would undergo solid directly to gas as sublimation. And I knew that because I was below that triple point here. Okay, so it's underneath the diagram. If I could blow that up for you somehow, it would have been like this. And I just crossed at a pressure below that triple point. Okay? Now, describe any changes when you take liquid argon from 10 atmospheres to 1 atmosphere at a constant temperature of 100 Kelvin. So now we're way out here at 100 Kelvin, and we're going from 1 atmosphere to, or excuse me, we're going from 10 atmospheres down below. So we're going to be definitely in the liquid phase. So in this one, we're taking liquid, and we're going to the vapor phase. and that's called vaporization. Now, this one's a little trickier. How do we tell the density? Well, it's all in that slope. So let's kind of draw our lines like that again. If the slope is leaning to the right, that means that my solid is more dense than my liquid. And the way you can do that is by looking at the freezing point relative to the triple point. Okay, so the freezing point was over here and the triple point was here. So if you compress it, if you increase the pressure, you go from gas to liquid to solid. So that means compression ends with solid last when you go right along there. Gas to liquid to solid. So that means the solid must be the most compressed. But a way that somebody taught me at a conference is this. If this slope leans to the right, righty-tighty, that means the solid is tighter or more dense than the liquid. Lefty-loosey, that means the solid is looser or less dense than your liquid, which is kind of unusual. Okay? So that is that one. Let me check our time here. And let's take a look at another one. We have enough time for one more. Observations. Again, we're talking about real gases at the molecular level and intermolecular forces. Those are keywords you want to underline. And so we're going to be looking at some claims, and we have to justify that claim. And the first one says is when we reduce the temperature, we reduce the volume. Now, a balloon has a flexible volume. And when you decrease the temperature, you're going to decrease the average kinetic energy, which means you have a decreased velocity. That in turn means that you're going to decrease the force or pressure on the surface of the balloon. And to maintain pressure inside equal to the outside, the volume shrinks. Okay? So it's all about equalizing the pressure inside and outside when you have a flexible volume there. Okay? Now, in this next one, I don't think I described that well, so I'll try to come up with a better example of that. Maybe I can find a better way to explain that. Right, but if you decrease the temperature, you decrease the kinetic energy and the velocity of the molecules, and the only way that we can maintain a constant pressure inside and out is for the velocity to decrease. All right, as we cool it further, the volume doesn't become zero. Well, why is that? Well, for one, molecules have a volume. It can't go to zero. But for another, every molecule has the potential for some sort of intermolecular forces. So as you decrease the temperature, you decrease the kinetic energy, and that increases the intermolecular forces of attraction that can be felt. So those attractions eventually make things solids and then liquids. Okay, the next one, I've got ammonia at one end. This is a fun little experiment when you can get it to work. The tubes have to be really, really dry. We used to do these experiments back in the day when we had a lot more time to teach stuff in pre-AP as well. Okay, so we've got ammonia at one end, and we've got HCl gas at the other end. And how we know where they've met is we're going to see this white ammonium chloride. It's going to be like a white cloud that forms. So the question is it going to be closer to the HCl end or the NH3 end? So it's a race, and it's one of those math formulas. If one car is at this speed and the other's at that speed, and they're driving towards one another, where are they going to meet? Well, remember, Graham's law says that the rate is proportional to 1 over the square root of the molar mass of the substance. So as you increase the molar mass, you decrease the rate. Well, this molar mass is about 17. This molar mass is on the order of 36. This is bigger and heavier. It's going to move slower. So if ammonia is moving faster, that ring is going to be much closer to the HCl. That's that ring of ammonium chloride. Will be closer to the HCl than it is to the ammonia. Okay? So that's why you see the ring closer. It's because rate is inversely proportional to molar mass. All right, we've got a few more topics we're going to clean up to help you with that take-home test and that intermolecular force activity. So until the next video, this is signing off.